Right now, at this exact moment, something is heading toward Venus. And in less than 72 hours, an interstellar visitor will pass closer to Earth's sister planet than most spacecraft ever have. Yet if you've been watching the news, scrolling through your feed, or even following space coverage, you've heard nothing about it. November 3rd, 2025. Mark that date. Because what happens on that day could rewrite everything we think we know about interstellar objects, orbital mechanics, and what's actually possible when something from beyond our solar system approaches a planet. This isn't speculation. This isn't science fiction. This is documented, confirmed, and happening whether anyone talks about it or not. And the silence. That's the first mystery we need to solve. Before we go any further, I need you to understand something. 3. I-Atlas, the interstellar comet that entered our solar system earlier this year, is about to make its second closest planetary approach. Not to Earth, not to Mars, to Venus. On November 3rd, 2025, at precisely 11:47 a.m. Universal Time, this object will pass within 0.65 astronomical units of Venus. That's approximately 97 million kilometers, or about 60 million miles if you're thinking in Earth terms. Now, I know what you're probably thinking. That sounds far. And you're right, it is far compared to, say, walking to your mailbox. But in astronomical terms, in the context of an interstellar object's trajectory through our solar system, this is remarkably, almost impossibly close. Here's what makes this so strange. When 3I Atlas was first confirmed as an interstellar visitor, the mainstream narrative focused almost entirely on its approach to the Sun, its speed, and the fact that it came from beyond our solar system. Media coverage highlighted its hyperbolic trajectory, its retrograde orbit, and the scientific excitement around observing an object from interstellar space. But buried in the technical papers, hidden in the trajectory calculations that most journalists don't read, is this Venus encounter. And it's not just a passing mention, it's a significant event, the second closest approach in the entire trajectory. Yet if you search for 3I Atlas Venus right now, you'll find academic papers, some technical forums, and almost zero mainstream coverage. Why? Let me give you some context. When Oumuamua, the first confirmed interstellar object, passed through our solar system in 2017, every major news outlet covered it. Scientists appeared on television. Documentaries were made. The public was fascinated. And Oumuamua didn't even come close to any planet. It just zipped through, gave us strange acceleration data, and left. But 3I Atlas, an object that will pass Venus at a distance closer than many artificial satellites orbit Earth relative to their planetary scale? Silence. And that silence is what should make you pause. Because either this encounter is being overlooked due to editorial oversight, or there's a reason it's not being emphasized. And I'm not sure which possibility is more concerning. Now, before you drop a comment saying I'm fear-mongering or creating conspiracy theories, let me be absolutely clear about what I'm claiming and what I'm not. I am not saying anything catastrophic will happen on November 3rd. I am not saying Venus is in danger. I am not saying there's a cover-up. What I am saying is this. A scientifically significant event is about to occur, and the lack of public discussion around it is unusual. Unusual enough that we should be asking why. Because when you look at the actual numbers, when you examine the trajectory data that's freely available through NASA's Horizon system and ESA's databases, this Venus encounter stands out. It's not just another point on the comet's path. It's a moment of gravitational interaction, potential observational opportunity, and depending on how you interpret physics, something that could provide answers to questions we've been asking since the moment we confirmed this object came from outside our solar system. So here's what I need from you right now. Before we continue, I want you to drop a comment below and tell me, did you know about the November 3rd Venus encounter before watching this video? Just a simple yes or no. Because I'm genuinely curious how many people are aware that this is happening, and if the answer is no, if this is the first time you're hearing that an interstellar object will closely approach Venus in less than 3 days, then that tells us something important about how information is being filtered, prioritized, or communicated. And that matters, because this isn't some obscure asteroid in the Kuiper Belt. This is an interstellar visitor, the third confirmed object from beyond our solar system, and it's about to interact with one of the most studied planets in our neighborhood. Let's talk about what makes this encounter scientifically significant. First, the distance. At 0.65 AU, 3i Atlas will be close enough to Venus that gravitational interaction becomes measurable. Not strong enough to alter Venus's orbit, let's be clear about that. Venus is a massive planet with 4.87 times 10 to the 24th kilograms of mass. A comet, even an interstellar one, isn't going to budge that. But the reverse? Venus will exert gravitational influence on the 3i Atlas, and depending on the comet's mass, composition, and velocity at that moment, that influence could alter its trajectory slightly. Scientists call this a gravitational slingshot or gravity assist, and while the effect will be minor, it will be measurable. Spacecraft tracking systems, ground-based telescopes, and orbital mechanics calculations will all be able to detect whether Venus changes Atlas's velocity, direction, or both. Second, the timing. November 3rd comes just 5 days after Atlas's perihelion, its closest approach to the Sun, which occurred on October 29th. At perihelion, the comet was subjected to maximum solar heating. That heating causes outgassing, ice sublimates into gas, dust gets released. The coma, the cloud of material around the nucleus, expands, and that activity can change a comet's trajectory through something called non-gravitational acceleration. We've seen this with other comets. Solar heating causes jets of gas to erupt from the surface, creating tiny thrust forces that push the comet slightly off its predicted path. Now, here's where it gets interesting. If Atlas is still experiencing significant outgassing on November 3rd, that activity could interact with Venus's gravitational field in ways that produce unexpected results. Not catastrophic, not dangerous, but unexpected. Measurable deviations from the predicted trajectory that scientists would then need to explain. Third, and this is what really separates the Venus encounter from just being another data point, this is the second closest approach in the entire trajectory. The closest approach was to Mars on October 3rd, when Atlas passed within 0.19 AU, about 28 million kilometers. That encounter happened. Scientists observed it. And as far as publicly available data tells us, nothing unusual occurred. Atlas passed Mars, continued on its trajectory, and the universe kept turning. But Venus is different. Venus has a much thicker atmosphere than Mars. Venus has stronger gravitational influence. And Venus, unlike Mars, is positioned in a way that makes spacecraft observation more feasible. Multiple satellites and probes, including ESA's JUICE spacecraft, NASA's STEREOA, and potentially others, will have line of sight to the encounter. That means data, real-time data, not theoretical models or post-event reconstruction, but actual observational measurements as the encounter happens. Now, here's the question that should be forming in your mind right now. If this encounter is scientifically significant, if it provides observational opportunities, if it represents the second closest approach to any planet in Atlas's entire journey through our solar system, why isn't it being discussed? Why are mainstream media outlets not covering it? Why haven't major science channels produced videos explaining what to expect? I've thought about this a lot over the past few weeks as I've been researching this topic, and I think there are a few possible explanations. 1. Editorial fatigue. The public has heard about interstellar objects before. Oumuamua was covered extensively. 2I Borisov, the second interstellar object, got significant attention. Maybe editors feel the story has been told. Maybe they think people are no longer interested. 2. Timing. November 3rd falls in a busy news cycle. Political events, economic concerns, cultural stories. Space news often gets deprioritized unless it's dramatic. And a comet passing Venus, while scientifically interesting, doesn't produce dramatic visuals or immediate threats that capture public attention. But there's a third possibility, and this is where I want you to think critically. Maybe the Venus encounter is being downplayed because scientists themselves are uncertain about what to expect. Let me explain what I mean. When you have a predictable event like a lunar eclipse or a meteor shower, scientists can confidently tell you what will happen, when it will happen, and what you'll observe. The models are solid. The predictions are reliable. But 3i Atlas? This object has already shown behaviors that don't perfectly match predictions. Its non-gravitational acceleration has been stronger than expected for a comet of its estimated size. Its brightness fluctuations have been irregular. And its trajectory, as we'll discuss in the next section, has statistical properties that make some researchers very uncomfortable. So maybe, and I'm speculating here, but it's educated speculation. Maybe the scientific community is taking a wait-and-see approach. Maybe they don't want to make predictions or statements that could be contradicted by observations. Maybe they're waiting for November 3 to happen, collecting the data, and then deciding what to say publicly. And if that's the case, if that's what's actually happening behind the scenes, then you and I are in a unique position right now. Because we're watching in real time, we're aware of the encounter before it happens. We have access to the same public databases, the same trajectory calculators, and the same observational tools that professional astronomers use. We just have to know where to look and what to look for. And that's exactly what this video is about. Not just explaining the Venus encounter, but giving you the framework to understand what's happening, why it matters, and what we should be watching for when November 3rd arrives. So let me tell you what we're going to do. Over the course of this video, I'm going to walk you through 7 key aspects of the Venus encounter. We're going to look at the trajectory patterns that led to this moment. We're going to examine the physics that govern what's possible when an interstellar object approaches a planet. We're going to discuss what actually happens during gravitational interaction at these distances. We're going to explore who's watching what spacecraft, what instruments, what organizations are collecting data. We're going to step into speculative territory and ask whether something beyond simple gravitational interaction could be occurring. And finally, we're going to prepare for November 3rd itself, giving you specific things to watch for, data sources to monitor, and questions to ask once the encounter happens. By the end, you'll understand not just what's happening, but why it matters and what comes next. Because November 3 isn't the end of this story, it's a chapter. And December 19th, when Atlas makes its closest approach to Earth, is the next one. But let's not get ahead of ourselves. First, we need to understand how we got here, how an interstellar object ended up on a trajectory that brings it this close to Venus, Mars, and Jupiter. And that's where mathematics becomes both fascinating and deeply unsettling. When Avi Loeb speaks, the scientific community listens, not always with agreement, not always with enthusiasm, but they listen. And there's a reason for that. Loeb isn't some fringe theorist operating out of a basement with a telescope and a conspiracy blog. He's the Frank B. Baird Jr., professor of science at Harvard University. He chaired Harvard's astronomy department for nearly a decade. He's published over 1,000 papers in peer-reviewed journals. He founded and leads the Galileo Project, a systematic scientific research program specifically designed to search for evidence of extraterrestrial technological artifacts. When someone with those credentials publishes an analysis suggesting that 3I Atlas exhibits trajectory characteristics inconsistent with random interstellar objects, you don't dismiss it. You examine it. And that's exactly what we're going to do right now. In early 2025, shortly after 3I Atlas's interstellar origin was confirmed, Loeb and his research team published a technical paper analysing the object's trajectory. The paper wasn't sensational. It didn't make wild claims. It presented mathematical analysis of the comet's approach distances to various planets in our solar system and calculated the statistical probability of such a trajectory occurring naturally. And here's what they found. 3I Atlas approaches Mars at 0.99 astronomical units. That's approximately 18 million miles or 28 million kilometers. It approaches Venus at 0.65 AU, the encounter we're discussing in this video, and it will approach Jupiter at 0.36 AU in March 2026, roughly 54 million kilometers. Now, taken individually, none of these encounters is impossible. Comets pass planets. Trajectories intersect orbital paths. This happens. But here's where the statistics become uncomfortable. Loeb's team calculated the probability of a randomly oriented interstellar object, meaning an object whose trajectory was determined by gravitational interactions in its origin system millions of years ago, not by any deliberate design approaching 3 inner planets at these specific distances. And the number they arrived at was approximately 0.05%. That's not 5%, that's 5,000ths of 1%. In practical terms, that's a probability of about 1 in 20,000. To put that in perspective, if you shuffled a standard deck of cards and drew 4 aces in a row, without replacement, the probability would be roughly 1 in 270,000. What Atlas is doing is less unlikely than that, but not by much. It's the astronomical equivalent of walking outside and finding a perfectly arranged stack of stones balanced on your doorstep. Could it happen naturally through wind, erosion, and random chance? Theoretically, yes. Would you bet money on that explanation? Probably not. Now, Before we go further, I want to address what this probability calculation actually means and what it doesn't mean. It does not mean that 3i Atlas is controlled. It does not mean that aliens are steering it. It does not prove intentional design. What it means is that the trajectory pattern is statistically unusual, and when scientists encounter statistically unusual patterns, they have two options. Option 1, accept that rare events occasionally happen, and this is one of them. The universe is vast. Interstellar space contains countless objects. Eventually, one of them was going to have a trajectory that looked unusual to us. That's the mainstream interpretation. It's reasonable, it's scientifically defensible, and it might be correct. Option 2. Examine whether the pattern suggests something beyond random chance. Not jumping to conclusions, not assuming alien intelligence, but asking whether there are physical mechanisms, natural or otherwise, that could produce such a trajectory more reliably than random stellar encounters. This is where Loeb's approach differs from many of his colleagues. Rather than immediately defaulting to the rare but possible explanation, he asks, what else could produce this pattern? And one of the possibilities he explores in his paper is what's called a directed panspermia trajectory. Now, hold on. Don't click away. I know how that sounds. But hear me out. Directed panspermia is a hypothesis, not a theory, not a claim, but a hypothesis that life might spread through the universe via deliberately sent biological payloads. The idea dates back to the 1970s, when Nobel laureate Francis Crick and chemist Leslie Orgel proposed it as one possible explanation for the origin of life on Earth. The hypothesis suggests that an advanced civilization might send spacecraft carrying microorganisms or genetic material to potentially habitable planets. These spacecraft would need trajectories that bring them close to multiple planets to maximize the chance of successful delivery. Now, I want to be crystal clear about what Loeb is and isn't claiming. He is not saying that 3i Atlas is a directed panspermia mission. He is not saying it carries biological payloads. What he is saying is that if such missions exist, their trajectories would look mathematically similar to what Atlas is doing. Close approaches to multiple planets, low delta velocity requirements for trajectory adjustments, and a path that maximizes planetary encounters while minimizing energy expenditure. He's not working backward from a conclusion. He's working forward from mathematics and asking what physical scenarios could produce these numbers. And one of those scenarios is not the only one, not the proven one, but one of them is deliberate design. Let me show you why mathematics matters. When an interstellar object enters a solar system, its trajectory is determined by three primary factors. 1. The velocity and direction it had when it left its origin system. 2. Gravitational interactions with stars and other massive objects it encountered during its millions of years travelling through interstellar space. 3. The gravitational field of our Sun once it enters the solar system. These factors create what's called a hyperbolic trajectory, a path that brings the object in, swings it around the Sun, and sends it back out into space. The shape of that trajectory is mathematically predictable. Given the object's velocity and angle of approach, you can calculate with high precision where it will go. And the vast majority of random hyperbolic trajectories don't bring objects close to multiple planets. Space is mostly empty. Planets occupy tiny fractions of the solar system's volume. So when an object happens to pass 3 planets at relatively close distances, the mathematics force you to ask, is this trajectory random, or was it shaped by something? And here's where Loeb's analysis becomes even more interesting. He didn't just calculate the probability of close approaches, he also analysed the delta velocity requirements for trajectory adjustments at each encounter point. Delta velocity, or dv, is the change in velocity needed to alter a trajectory. If you wanted to turn 3i Atlas's Venus flyby into a Venus intercept, meaning a collision course, how much dv would you need? And the answer, according to the calculations, is less than 10 kilometers per second until the end of July 2025. For Mars, it was less than 5 km/h until the end of July. For Jupiter, it's less than 5 km/h all the way until November 2025. Now, why do these numbers matter? Because 5 kilometers per second is achievable with chemical rocket propulsion. It's the velocity change that intercontinental ballistic missiles from the 1960s could accomplish. It's within the range of technology that humanity has possessed for over half a century. Let me put this in perspective. If 3i Atlas were a spacecraft, and I'm speaking hypothetically here, and if it wanted to deploy probes or secondary objects toward Venus, Mars or Jupiter, the energy requirements would be surprisingly modest. At the Venus encounter point, a small thruster firing lasting just a few seconds could release an object that would then fall toward Venus under gravitational attraction. That object wouldn't need to be powered all the way to the planet. Gravity would do most of the work. The same applies to Mars and Jupiter. The trajectory that Atlas follows naturally creates low-energy windows for planetary access, and that's what makes the trajectory pattern so mathematically intriguing. It's not just that Atlas passes near planets. It passes near planets at moments when altering course to reach those planets would require minimal energy. Now, the mainstream astronomical community looks at these same numbers and arrives at a different interpretation. They say, yes, the probability is low, but not impossibly low. Yes, the DV requirements are favourable, but that's a consequence of the trajectory, not evidence of design. And yes, the pattern is interesting, but interesting isn't the same as impossible. Natural processes can produce unlikely outcomes. That's the nature of probability. And they're right. Statistically unlikely events happen all the time. Someone wins the lottery, lightning strikes the same place twice, you run into an old friend in a foreign country. None of these events are impossible. They're just improbable. And improbable things happen when you have enough opportunities for them to occur. The universe provides trillions upon trillions of opportunities. So occasionally you get an interstellar object with a trajectory that looks designed, even though it's actually random. This is the tension at the heart of the scientific debate. Not whether the trajectory is unusual, everyone agrees it is. Not whether the numbers are correct, the mathematics is public and verifiable. The debate is over interpretation. How do you distinguish between rare but natural and potentially artificial? What threshold of improbability moves something from interesting coincidence to requires alternative explanation? And who gets to decide where that threshold lies? These are philosophical questions as much as scientific ones, and they don't have easy answers, which is why Loeb's approach is both valuable and controversial. He's willing to ask questions that make colleagues uncomfortable. He's willing to present hypotheses that might be wrong, because in his view, science progresses by examining uncomfortable possibilities, not by defaulting to the safest explanation. But here's what I find most compelling about this entire discussion. Regardless of whether you think Atlas's trajectory is random or designed, everyone agrees on the underlying facts. The close approaches are real, the delta velocity calculations are accurate, the statistical improbability is documented. What we're debating is interpretation, and that's actually where science gets interesting. Because interpretation requires judgment. It requires weighing competing explanations. It requires deciding how much weight to give to prior assumptions versus new data. And it requires intellectual humility and the recognition that our current understanding might be incomplete. That's the space we're operating in right now. Not certain knowledge, not proven theories, but careful analysis of unusual patterns combined with openness to multiple explanations. So as we move forward into the next section, where we'll examine the physics of what Atlas can actually do at these distances, I want you to hold this tension in mind. The trajectory pattern is unusual, that's established. What it means is open for interpretation, and the Venus encounter on November 3rd will add one more data point to this puzzle. Because if Atlas's trajectory changes in unexpected ways after the Venus approach, if velocity measurements don't match predictions, if the object's path deviates from calculated models, then the conversation about random versus designed becomes more than theoretical, becomes observational. And observation is what separates speculation from science. Now we need to talk about something that most space coverage completely skips over. And I understand why it's technical. It requires understanding orbital mechanics, and it doesn't produce dramatic visuals for television. But if you want to genuinely understand what makes 3I Atlas's trajectory so significant, you have to understand delta velocity physics. So I'm going to explain this as clearly as I can, using analogies where helpful, but not dumbing it down to the point where the meaning gets lost. Because the physics here is precisely what separates interesting coincidence from, wait, how is that even possible? Let's start with the fundamental concept. Delta velocity, written as dv in physics notation, is the change in velocity needed to alter a trajectory. Every trajectory in space is governed by gravity and momentum. An object moving through space will continue on its current path unless a force acts on it. That force could be gravity from a nearby massive object like a planet or star, or it could be thrust from a propulsion system, a rocket engine, ion drive, or any mechanism that expels mass to create acceleration. When you want to change where an object is going, you need to change its velocity, and the amount of change required is the delta velocity. Simple concept, profound implications. Here's why DV matters in the context of 3i Atlas. Every point along the comet's trajectory has a different DV requirement for reaching any given destination. If you wanted to divert Atlas to crash into Venus, for example, the energy cost would depend entirely on when and where you apply thrust. Try to do it when Atlas is far from Venus and moving at high speed relative to the planet. You'd need enormous DV because you're fighting the comet's existing momentum and trying to bend a fast-moving trajectory sharply. But try to do it when Atlas is naturally approaching Venus, when the gravitational pull is already working in your favour. The DV requirement drops dramatically, and that's exactly the situation we're observing on November 3rd. According to the trajectory analysis published by Loeb's team, and independently verifiable through NASA's Horizon system, the DV required to intercept Venus from 3i Atlas's trajectory was less than 10 km per second through the end of July 2025. Now, let me put that number in context. Chemical rockets, the kind that launched humans to the moon, the kind that launched satellites today, the kind that are essentially controlled explosions directing thrust through a nozzle, can achieve delta velocities of approximately 5 to 9 km per second, depending on their design and fuel. That means the Venus intercept window from Atlas's trajectory falls within the capability range of conventional rocket technology, not exotic physics, not theoretical propulsion systems, technology that existed in the 1960s. The Mars numbers are even more striking. The DV requirement for Mars intercept was less than 5 km per second until the end of July, and for Jupiter, it remains below 5 km all the way until November 2025. These aren't arbitrary numbers I'm pulling from speculation. These are calculated values based on orbital mechanics equations that have been tested and verified through decades of spacecraft missions. When NASA sends a probe to Mars, their engineers use these exact same calculations to determine launch windows, trajectory corrections, and fuel requirements. The physics is settled. What's unsettling is how perfectly Atlas's natural trajectory creates low-energy windows for multiple planetary approaches. Now let's talk about why low DV matters beyond just intercepts. There's another concept in orbital mechanics called the Oberth effect, and this is where things get really interesting. The Oberth effect describes how the efficiency of propulsion changes depending on where in a trajectory you apply thrust. Specifically, thrust applied when you're moving fast relative to a massive object produces more change in total energy than the same thrust applied when you're moving slowly. Think of it this way. If you're driving a car on a highway at 70 miles per hour and you press the accelerator, you're adding speed to an already fast-moving object. That additional speed gets amplified because of your existing momentum. The same thing happens in space, but the effect is much more pronounced near massive objects, where gravitational potential energy is high. When 3i Atlas passed through perihelion on October 29th, it was moving at its fastest velocity relative to the Sun, approximately 68 km per second. At that speed, at that distance, the Oberth effect is maximized. A small thrust applied during perihelion passage produces the largest possible change in the object's trajectory. This is why spacecraft performing interplanetary missions often do their major engine burns when passing close to the Sun or a planet. They're taking advantage of the Oberth effect to maximize efficiency. And here's what makes Atlas's trajectory so mathematically elegant. Its perihelion passage on October 29th was just 5 days before the Venus encounter on November 3rd. That means any trajectory adjustments made near perihelion when the Oberth effect is strongest would have their maximum impact right around the time of the Venus approach. Let me be explicit about what I'm saying and what I'm not saying. I am not claiming that 3i Atlas fired thrusters at perihelion. I am not saying that trajectory adjustments occurred. What I am saying is that the timing and geometry create an optimal window for such adjustments if they were to occur, and that optimality is part of what makes the overall trajectory pattern statistically unusual. Because remember, we're not just talking about one close approach, we're talking about multiple close approaches, each occurring at energetically favourable moments, creating a sequence of low DV windows that span several months. That's the pattern. That's what mathematics describes, and that's what pushes the probability down to 1 in 20,000. Now let's consider another aspect of low DV mechanics that rarely gets discussed in popular space coverage: probe deployment. If you wanted to send a secondary object from Atlas toward Venus, You wouldn't need to accelerate it to 10 kilometers. You'd only need to give it a small relative velocity, essentially pushing it off the comet's trajectory in the direction of Venus. Once released, the probe would follow its own ballistic trajectory, gradually diverging from the comet's path. Venus's gravity would do the rest, pulling the probe into a closer approach or potentially an intercept. The energy cost for that initial push, the separation velocity, would be a fraction of the intercept EV. We're talking 1 or 2 kilometers per second, possibly less depending on the exact geometry and timing. This kind of probe deployment is not theoretical. It's exactly how humanity explores the solar system. When NASA's Cassini mission arrived at Saturn, it carried the Huygens probe, which was released on a trajectory toward Titan. Cassini didn't have to burn fuel all the way to Titan's surface. It just released Huygens at the right moment with the right velocity, and gravity handled the rest. The same principle applies to any object approaching Venus from Atlas's trajectory. A small push at the right moment creates a divergent path. And because Atlas's trajectory naturally brings it close to Venus with favourable geometry, the energy cost for that push remains low. Again, I'm not claiming this is happening. I'm explaining the physics of what would be possible if it were to happen. There's also the reverse scenario to consider, and this is where the Oberth effect becomes even more interesting. What if an object wanted to slow down rather than speed up? What if the goal wasn't to pass through the solar system and leave, but to capture into a bound orbit around the Sun or one of the planets? Normally this requires enormous dV because you're fighting the object's hyperbolic trajectory and its natural tendency to escape the Sun's gravity after perihelion. But if you apply thrust at perihelion when velocity is highest, the Oberth effect works in your favour even for deceleration. You can shed velocity more efficiently, potentially capturing into an elliptical orbit. Scientists call this a reverse solar Oberth maneuver, and while it would still require significant dV more than a simple intercept, the perihelion location makes it more feasible than attempting the same maneuver anywhere else along the trajectory. Why does this matter for the Venus encounter? Because November 3rd represents not just a close approach, but a gravitational interaction opportunity. Venus itself can alter Atlas's trajectory through what's called a gravity assist or gravitational slingshot. This is a well-understood phenomenon. When a spacecraft passes close to a planet, it can gain or lose velocity relative to the Sun depending on the geometry of the encounter. Pioneer, Voyager, Cassini. Nearly every deep space mission has used gravity assist to reach distant destinations without carrying impossible amounts of fuel. The planet's gravity pulls the spacecraft, changing its direction and speed. And while the effect on a comet passing at 0.65 AU from Venus will be much smaller than a close spacecraft flyby, it won't be zero. There will be some velocity change, and that change will be measurable. Here's where the observational opportunity becomes crucial. If Atlas's post-Venus trajectory matches predictions exactly, within measurement tolerances, then we can confidently say that only natural gravitational interaction occurred. The change in velocity will be precisely what Newton's and Einstein's equations predict for an object of Atlas's estimated mass passing Venus at that distance and speed. But if there's a deviation, if the velocity changes slightly more or slightly less than predicted, or if the direction changes in ways that don't match pure gravitational calculations, then scientists have to explain that discrepancy. Maybe the comet's mass was estimated incorrectly. Maybe outgassing from solar heating produced thrust at an unexpected moment. Or maybe, and this is the speculative threshold, something else contributed to the velocity change. The reason I'm spending so much time on these technical details is because they form the foundation for everything else we're going to discuss. When people casually say it's just a comet passing a planet, they're missing the layers of physics that make this encounter meaningful. Yes, it's a comet. Yes, it's passing a planet. But the specific distance, the timing relative to perihelion, the low dV windows, the gravitational interaction potential, the Oberth effect opportunities, all of these factors combine to create a scenario that's rich with physical possibilities, and those possibilities are constrained by mathematics. We're not speculating wildly. We're working within the boundaries of established orbital mechanics, asking what's physically possible given the known parameters. And here's the final piece of this physics discussion that ties everything together. All of these low dV windows, all of these energetically favourable moments, they're time-limited. The Venus intercept window closed at the end of July. The Mars window closed in July as well. The Jupiter window extends into November, but even that will eventually pass. Once Atlas moves beyond these approach distances, once the geometric alignment changes, the DV requirements skyrocket. What might have required 5 km in July could require 50 km in December. That's the nature of orbital mechanics. Opportunities open and close based on position and velocity. And the trajectory that Atlas follows naturally creates a sequence of opportunities that cluster within a narrow time frame. Improbable? Yes. Impossible? No. But the distinction between improbable and impossible is exactly where scientific debate lives. So as we transition to discussing what actually happens during the Venus encounter, the gravitational effects, the potential for outgassing, the scenarios that scientists are and aren't talking about, keep this physics framework in mind. Every scenario we'll discuss is bounded by delta velocity constraints. Every possibility is evaluated against what the mathematics allows. We're not abandoning science for speculation. We're using science to map the boundaries of what's possible, and sometimes the most interesting discoveries happen right at those boundaries. November 3rd, 2025, 11:47 anti-meridian Universal Coordinated Time. Convert that to your local time zone, mark it on your calendar, and understand that at that precise moment something will happen. Not something catastrophic, not something that will make headlines or create visible effects you can see from Earth's surface, but something measurable. Something that changes the trajectory of an interstellar object as it passes within 97 million kilometers of Venus. And the question we need to answer is, what exactly does something mean in this context? Let's start with what we know will definitely happen, based on physics that's been tested and verified through hundreds of spacecraft missions and natural observations. As 3I Atlas approaches Venus, it enters the planet's gravitational sphere of influence. Now, that phrase sphere of influence has a specific technical meaning in orbital mechanics. It's the region around a planet where that planet's gravity dominates over the Sun's gravity in determining a smaller object's trajectory. For Venus, that sphere of influence extends to about 616,000 kilometers from the planet's center. Since Atlas is passing at 97 million kilometers, it never actually enters Venus's sphere of influence. It remains in a solar orbit throughout the encounter. Venus's gravity affects it, but doesn't capture it. Think of it as feeling the pull of a magnet while you're walking past it. You feel the force. It might alter your path slightly, but it doesn't grab you and hold you. So what does Venus's gravity do to Atlas? It changes the comet's velocity relative to the Sun, both the speed and the direction. Imagine you're driving north on a highway at 100 km per hour, and a strong crosswind from the east hits your car. Your speedometer might still read 100, but your actual path curves slightly westward, and your velocity relative to the ground now has both northward and westward components. Venus's gravity works similarly. Atlas approaches with a certain velocity vector magnitude and direction. Venus's gravitational pull adds a component to that vector, changing both where Atlas is heading and how fast it's moving. The magnitude of this change depends on 4 factors: Venus's mass, Atlas's mass, the distance of closest approach, and the relative velocity between them. Here's what makes this calculable. We know Venus's mass with extraordinary precision, 4.867 times 10 to the 24th kilograms. We know the approach distance, 0.65 AU, or 97.2 million kilometers. We know Atlas's velocity relative to the Sun is approximately 68 kilometers during this period. The only significant uncertainty is Atlas's mass, and even there, we have estimates based on its brightness, assumed albedo, and observed coma activity. So astronomers can calculate with reasonable confidence what velocity change should occur. They can predict how much Venus's gravity will bend Atlas's trajectory, and then, after November 3rd, they can measure what actually happened. The comparison between prediction and observation is where science happens. Now, let's add the next layer of complexity: outgassing. Comets aren't inert rocks. They're mixtures of ice, rock, and organic compounds. When sunlight heats the surface, ice's sublimate transition directly from solid to gas without passing through the liquid phase. That gas escapes into space, carrying dust particles with it, creating a visible coma and sometimes a tail, and that escaping gas creates thrust. Not a lot of thrust, nothing like a rocket engine, but enough to measurably affect the comet's trajectory over time. Scientists call this non-gravitational acceleration, and it's been observed and measured for dozens of comets throughout the solar system. 3i Atlas has been showing non-gravitational acceleration since before perihelion. Observations documented that its brightness increased as it approached the Sun, indicating active outgassing, and the pattern of that outgassing where on the nucleus it's most intense. Which direction the jets point affects how much thrust is created and in what direction. Here's why this matters for November 3rd. Atlas passed perihelion on October 29th, when solar heating was at maximum. 5 days later, on November 3rd, it's still close to the Sun, still experiencing strong heating, and presumably still outgassing. That means during the Venus encounter, two forces are acting on the comet simultaneously: Venus's gravitational pull and the thrust from outgassing. Disentangling these two effects in post-encounter data is going to be challenging. Did the velocity change more than predicted because outgassing was stronger than estimated, or did something else contribute? Let me walk you through the observational scenarios that scientists are preparing for. I'm going to present these as a spectrum from most conventional to most speculative, and I want you to understand that all of these are physically possible. They just have different levels of probability and different implications for our understanding of Atlas. Scenario A, standard gravitational encounter. This is the baseline expectation. Atlas passes Venus at 0.65 AU. Venus's gravity bends the trajectory by a small amount, probably less than 0.1 degrees in direction, less than 1 km/s in velocity. Outgassing is consistent with previous observations, contributing an additional small component to trajectory change. Spacecraft instruments measure these changes, scientists compare with predictions, and the numbers match within error bars. Conclusion: nothing unusual happened. Atlas is a comet behaving like comets behave. The encounter was exactly as expected. This is what mainstream astronomy considers most likely. Scenario B, unexpected velocity anomaly. In this scenario, post-encounter measurements show a velocity change that doesn't quite match predictions. Maybe the change is larger than Venus's gravity alone should produce. Maybe it's in a slightly different direction than pure gravitational interaction would cause. Scientists examine the discrepancy and propose explanations. Perhaps Atlas's mass was estimated incorrectly. Perhaps the outgassing model needs refinement. Perhaps there was a brief period of intense jet activity that wasn't captured in earlier observations. None of these explanations would be alarming or require exotic physics. They just indicate that our models need adjustment. This scenario is less likely than Scenario A, but still well within the realm of conventional science. Scenario C, fragmentation detection. Comets sometimes break apart. We've seen it happen. Comet Shoemaker-Levy 9 famously fragmented into multiple pieces before colliding with Jupiter in 1994. Thermal stress, tidal forces, structural weakness, any of these can cause a comet nucleus to crack and split. If fragmentation occurred to Atlas before or during the Venus encounter, telescopes would detect multiple objects instead of a single nucleus. Each fragment would follow a slightly different trajectory, creating a spread pattern. Post-encounter observations would show a debris field rather than a discrete object. Now, there's currently no evidence that Atlas is fragmenting. But the stress of perihelion passage combined with the gravitational tug from Venus creates conditions where fragmentation becomes more likely, not certain, just more likely than during quieter periods of the orbit. Scenario D, atmospheric interaction signal. This one is highly speculative and probably unlikely, but it's worth mentioning for completeness. Venus has a thick atmosphere extending high above its surface. The exosphere, the outermost layer, extends to tens of thousands of kilometers. Atlas is passing millions of kilometers away, so direct atmospheric interaction is essentially impossible. But if the comet is releasing gas at high rates, and if Venus's magnetic field interacts with that gas in unusual ways, infrared satellites might detect faint perturbations. This would be extraordinarily difficult to observe, and would require instruments specifically looking for it. I'm including this scenario not because I think it's likely, but because it illustrates how even a simple planetary approach can have multiple physical effects that cascade in subtle ways. Now here's the crucial question that separates casual observation from scientific measurement. How do we know which scenario occurred? The answer is data. Multiple data sources collected by different instruments cross-checked and verified. NASA's Stereo A spacecraft has been tracking Atlas and will have observational data from the encounter period. ESA's JUICE spacecraft, which we'll discuss in detail in the next section, will collect measurements. Ground-based telescopes, both professional observatories and advanced amateur equipment, will be pointed at Atlas around November 3rd, and all of this data will be compared with pre-encounter predictions. The trajectory models say Atlas should be at position X with velocity y at time z. Observations after the encounter will show whether it actually is at position X with velocity y at time z. If yes, scenario A. If no, we move into scenarios B through D. But there's a temporal dimension here that I need you to understand. The data doesn't arrive all at once. Spacecraft transmissions take time to reach Earth. Light travel time at the distance. Stereo A is operating means there's a delay between when observations are made and when they're received. Ground-based telescopes can observe in near real time, but processing the data, reducing images, extracting position measurements, and calculating velocity vectors takes hours to days. And then there's the institutional process. Scientists don't typically release preliminary findings immediately. They check their work, they consult with colleagues, they write up results for peer review. So even though the Venus encounter happens on November 3rd, we might not have definitive conclusions about what occurred until November 5th, or November 7th, or later. And that gap between event and understanding is where speculation thrives. This is actually one of the reasons I wanted to make this video before November 3 rather than after. Because right now, we can discuss what to expect, what to look for, what the possibilities are, all without the noise of preliminary reports and conflicting interpretations. After November 3rd, everyone will have opinions. Social media will be full of claims and counterclaims. Some people will say nothing unusual happened, others will insist they detected anomalies, and sorting truth from noise will be difficult. But if you understand the physics beforehand, if you know what data matters and what's just speculation, you'll be in a much better position to evaluate the claims as they emerge. Let me give you one more layer to think about. The Venus encounter isn't isolated. It's one point in a continuous trajectory. Atlas approached Mars on October 3rd. Now it approaches Venus on November 3rd. Then it continues toward Earth, reaching closest approach on December 19th at 180 AU, much farther than Venus but still the closest approach to our planet. And then in March 2026, it approaches Jupiter at 0.36 AU. Each of these encounters is a measurement opportunity. Each one provides data about how Atlas is moving, how its trajectory is changing, whether its behavior matches predictions. And it's the pattern across all these encounters that will ultimately tell us whether Atlas is just an ordinary interstellar comet or something more unusual. So when November 3rd happens, when the Venus encounter occurs, don't expect drama. Don't expect visible explosions or trajectory changes you can watch in real time. Expect measurements, expect data, expect scientists carefully comparing what they observe with what they predicted, and expect that initial conclusions might be cautious, hedged with uncertainty, qualified with error bars. Because that's how science works when examining something we've never seen before. We don't jump to conclusions, we accumulate evidence. And the Venus encounter is one piece of evidence in a larger puzzle that spans the entirety of 3i Atlas's journey through our solar system. There's a spacecraft currently travelling through the inner solar system that most people have never heard of, and it's about to play a role in one of the most interesting astronomical observations of the year. ESA's Jupiter Icy Moons Explorer, universally called JUICE, launched on April 14, 2023, beginning an 8-year journey to Jupiter, where it will study Ganymede, Callisto, and Europa, 3 of the gas giant's largest and most scientifically intriguing moons. JUICE carries some of the most sophisticated scientific instruments ever launched on a planetary mission. Magnetometers to measure magnetic fields, particle detectors to analyze the radiation environment, infrared spectrometers to map surface composition, and radar systems capable of penetrating ice. And right now, as JUICE travels along its trajectory toward an Earth gravity assist in November 2024 and eventual arrival at Jupiter in 2031, it has line of sight to 3i Atlas during the Venus encounter. Now, let me be clear about what this means and what it doesn't mean. JUICE wasn't designed to study comets. Its instruments were built and calibrated for Jupiter's environment. The spacecraft's trajectory was planned years before 3i Atlas was discovered, so there was no deliberate positioning to observe this particular encounter. But opportunity science is a standard part of space exploration. When a spacecraft happens to be in the right place to observe something interesting, mission planners take advantage. They adjust instrument pointing, they modify observation schedules, they collect ancillary data that wasn't part of the primary mission but might yield valuable scientific insights. And that's exactly what's happening with JUICE and ATLAS. Here's why this matters. JUICE's instruments can detect things that ground-based telescopes struggle with or miss entirely. For example, the Particle Environment Package, called PEP, measures charged particles, electrons, protons, ions in the surrounding space. If ATLAS is actively outgassing during the Venus encounter, some of that gas will be ionized by solar radiation, creating charged particles that PEP could potentially detect. That would provide direct measurements of the comet's activity level, composition, and outgassing rate at the exact time of Venus's closest approach. Similarly, JUICE's magnetometer can measure disturbances in the local magnetic field, caused by interaction between the solar wind and gas from the comet's coma. These measurements wouldn't tell us everything about ATLAS, but they'd tell us things that optical telescopes can't. Now, here's where the situation gets interesting from a public information perspective. As I'm recording this on October 31st, there has been no official ESA press release announcing that JUICE will observe ATLAS during the Venus encounter. No news articles from major science outlets. No statements from mission scientists explaining what data will be collected. And that absence is notable, not because it indicates anything sinister or secretive space agencies don't announce every minor observation schedule adjustment, but because it represents a communication gap. If JUICE does collect data on ATLAS, and if that data shows something unexpected, the public's first awareness might come weeks or months later when results appear in a scientific paper. And by then, the opportunity for real-time communal observation, for public engagement with the science as it happens, will have passed. This pattern isn't unique to JUICE or ESA, it's endemic to how modern space science operates. Spacecraft generate enormous amounts of data. That data gets downlinked to Earth, processed by specialized software, analyzed by scientists, checked for errors, compared with models, and eventually published in peer-reviewed journals. The time between observation and publication can be months or years. And for ancillary observations, measurements that weren't part of the primary mission plan, that timeline often stretches even longer, because they're lower priority than the core science objectives. So there's a built-in delay between what spacecraft observe and what the public learns, and during that delay, the only people who know what's happening are the mission teams. Let me paint you a specific scenario to illustrate why this matters. Imagine that on November 3rd, JUICE's particle detectors register an unexpected spike in ionized material near ATLAS's predicted position. Mission scientists see this data within 24 to 48 hours as telemetry is downlinked and processed. They immediately start analyzing it, trying to determine what caused the spike. Is it normal outgassing? Is it fragmentation? Is it an instrumental artifact? They run models, check calibrations, and consult with colleagues. This process takes weeks. Meanwhile, the public knows nothing. No press release has been issued because scientists don't publicize preliminary findings that might be wrong. Finally, 2 months later, a paper gets submitted to a journal describing the observation. 3 months after that, the paper passes peer review and gets published. So by March 2026, the public learns that something unusual was detected during the November 2025 Venus encounter. But the moment of discovery, the initial detection, the real-time something just happened experience, the public missed all of that. Now, I'm not criticizing this process. Peer review exists for good reasons. Scientific rigor requires verification before publication. Announcing preliminary findings that later prove false damages credibility. But I'm pointing out that this institutional structure creates information asymmetry. The people operating the instruments know more sooner than the people funding the missions. And when you're dealing with something as unusual as an interstellar object, something that generates public interest and curiosity, that asymmetry can feel frustrating. It can feel like gatekeeping, even when it's actually just the normal pace of careful science. So what can we actually expect from JUICE regarding the Atlas-Venus encounter? Let me be realistic about capabilities and limitations. JUICE is currently millions of kilometers from both Venus and Atlas. It's not doing close-range flybys. It's not positioned for high-resolution imaging. What it can provide is in situ measurements of the space environment in that region of the inner solar system during the encounter period. If Atlas's coma is extensive enough, if outgassing is strong enough, JUICE might detect the outer edges of the coma's particle signature. Emphasis on might. This isn't guaranteed. It depends on how active Atlas is, what direction the coma is pointing, and how sensitive JUICE's instruments are to those particular signatures. But even a null result detecting nothing unusual would be scientifically valuable because it would constrain estimates of Atlas's activity level. There's another spacecraft I need to mention here, NASA's STEREOA. STEREOA is part of a 2-spacecraft mission originally designed to study the Sun from multiple angles. One of the pair, STEREOB, lost contact years ago, but STEREOA continues operating and has been tracking 3I Atlas as the comet moves through the inner solar system. STEREOA carries heliospheric imagers and wide-field cameras that can detect faint objects against the background glow of the Sun's corona. And because STEREOA's orbit positions it with a different viewing angle than Earth, it can observe parts of Atlas's trajectory that are difficult to see from ground-based telescopes. So between JUICE and STEREOA, there are at least 2 spacecraft with observational capability during the November 3 encounter. But here's the reality. We might not get any spacecraft data released publicly for weeks. And even when data is released, it might be raw telemetry that requires specialized knowledge to interpret. The pretty pictures, the graphs, the scientific summaries that make findings accessible to non-experts come later, after data reduction and analysis. So if you're hoping to see spacecraft footage of the Venus encounter in real time, that's probably not going to happen. What we'll get instead is ground-based telescope observations, amateur astronomer reports, and eventually spacecraft data after processing. Now, I want to address a question that I know some of you are thinking. Could there be classified observations? Could military satellites or Defense Department assets be watching Atlas and keeping results secret? The honest answer is possibly, but unlikely to matter. Military satellites are optimized for observing Earth-tracking missiles, monitoring facilities, and providing reconnaissance. They're not designed for deep space observation. And while it's true that some military telescopes also track satellites and orbital debris, their capabilities for observing an object at Atlas's distance would be similar to civilian observatories. Could they be watching? Maybe. Would they detect things that civilian observers miss? Unlikely. Would they release data publicly? Even more unlikely. So while I acknowledge the theoretical possibility of classified observations, I don't think it's a significant factor in understanding what happens on November 3rd. What is significant is the growing network of amateur astronomers with serious observational capability, high-end amateur telescopes equipped with CCD cameras, spectrographs, and automated tracking systems can now collect data that rivals professional observatories from a few decades ago. And those amateur observers share data openly on forums, on social media, on sites like the Minor Planet Center and the Central Bureau for Astronomical Telegrams. So even if ESA or NASA delays releasing spacecraft data, we'll have independent observations from multiple sources. That's actually one of the healthiest aspects of modern astronomy. Science is no longer locked behind institutional walls. Verification comes from distributed observers who don't all work for the same organization. So here's what I'm watching for in the days following November 3. First, amateur astronomer reports on forums like Cloudy Nights, the Asteroids and Remote Planets subforum on MPML, and Twitter hashtags like 3I Atlas and Interstellar Comet. These reports will appear within hours to days of the encounter and will give us the earliest indications of whether anything unusual was observed. Second, ESA's official press releases and blog updates. If something significant was detected by JUICE, ESA will eventually announce it, though the timeline is uncertain. Third, NASA's Asteroid Watch social media accounts and the JPL Small Body Database updates. If Atlas's trajectory changes measurably, those databases will be updated with revised orbital elements. And fourth, preprint servers like ARCiv, where scientists often upload papers before formal peer review. If researchers observe something interesting, they'll write it up and post it to Archive to establish priority and get feedback from colleagues. All of these sources are publicly accessible. You don't need institutional affiliation. You don't need to wait for media coverage. You can go directly to the data as it becomes available. And that's what I'll be doing starting November 3rd. Monitoring those sources, looking for signals in the noise, trying to separate genuine observations from speculation and misinterpretation, because in the immediate aftermath of an unusual event, there's always confusion, always conflicting reports, always people claiming they saw things that might or might not be real. The skill is in knowing what to trust, what to doubt, and what to wait for verification on, and that's exactly the skill we're going to exercise together as this unfolds. We've reached the point where we need to talk about something that most mainstream science coverage won't touch, and I need to be absolutely clear about the epistemological boundaries before we proceed. What I'm about to discuss is speculative. It's grounded in physics. It's consistent with orbital mechanics. But it's not proven, not observed, and not the consensus explanation for what 3I Atlas is or what it's doing. This is the threshold between documented science and theoretical possibility. And crossing that threshold requires intellectual honesty about what we know versus what we're hypothesizing. So let me frame the question precisely. Given that 3I Atlas approaches Venus with low delta velocity requirements, given that its trajectory creates energetically favorable windows for planetary access, and given the statistical improbability of such a trajectory occurring naturally, is it theoretically possible that Atlas could release secondary objects, probes, or payloads toward Venus? Not asking if it's probable, not asking if there's evidence, asking if it's physically possible. The answer is yes, unambiguously yes. The physics permits it. Now let me explain what that means and what it doesn't mean. When a spacecraft or any object releases a secondary payload, it requires two things: a separation mechanism and a relative velocity. The separation mechanism can be as simple as a mechanical spring that pushes two objects apart, or as complex as an explosive bolt system. The relative velocity is the speed at which the two objects move away from each other after separation. For probe deployment toward a planet, you need enough relative velocity to place the probe on a diverging trajectory that intersects the planet's gravitational sphere of influence, and as we discussed in the delta velocity section, the required relative velocity depends entirely on where in the trajectory you perform the separation. At Atlas's November 3rd closest approach to Venus, the delta velocity required to intercept Venus is less than 10 kilometers per second. But probe deployment doesn't require intercepting from Atlas's exact position at closest approach. It requires intercepting from wherever the probe is, when it separates. If Atlas released a probe days or weeks before November 3rd, when it was farther from Venus but still within a favourable geometric window, the separation velocity could be even lower. The probe would then spend days coasting on its ballistic trajectory, gradually diverging from the comet's path until Venus's gravity becomes the dominant force guiding it toward the planet. This is exactly how we've delivered payloads to planets throughout the history of space exploration. Voyager's probe releases, Cassini's Huygens lander, Mars rovers carried inside entry capsules. The principle is identical, just scaled to different missions. So here's the speculative scenario, presented with full acknowledgement that this is a hypothesis, not observation. If 3I Atlas were not merely a natural comet, but a deliberately designed interstellar probe, a scenario that Avi Loeb has discussed as physically plausible, though unproven, then the trajectory it's following would be nearly optimal for delivering secondary payloads to Venus, Mars, and Jupiter using minimal energy. The close approaches at low delta velocity windows create separation opportunities. The timing relative to perihelion maximizes Oberth effect efficiency. The retrograde orbit orientation provides gravitational assists that natural prograde trajectories wouldn't offer. It's an elegant design from an orbital mechanics perspective. Too elegant, some would argue, to be coincidental. But let me immediately present the counter-argument, because intellectual honesty requires examining both sides. Natural processes can produce elegant outcomes. Evolution creates biological systems of extraordinary complexity and efficiency without any deliberate design, just selection pressure over millions of generations. Planetary formation creates orbital resonances that look mathematically perfect, but arise from gravitational interactions over billions of years. The Fibonacci sequence appears in sunflower seed patterns not because plants are mathematicians, but because that arrangement maximizes packing efficiency through simple growth algorithms. So elegance alone doesn't prove design. It might just reflect physical laws operating under specific constraints. An Atlas's trajectory, while statistically unusual, could be the natural result of its origin system's stellar configuration, the gravitational kicks it received during formation, and chance encounters during millions of years travelling through interstellar space. Here's where the scientific debate becomes philosophical. At what point does statistical improbability become evidence of design rather than just rare coincidence? Biologists struggled with this question for decades when examining complex organs like eyes. How could something so sophisticated arise through random mutation? The answer turned out to be that it wasn't random, it was selected. Beneficial mutations accumulated, harmful ones died out, and over enough generations, complexity emerged. But we can observe biological evolution in real time now through experiments with bacteria and fruit flies. We can test the mechanisms. For Atlas, we can't. It's a sample size of 1. We can't rerun the simulation with different initial conditions and see if similar trajectories emerge frequently or rarely. We only have the one trajectory we're observing, and we have to decide whether it's coincidence or something more. Let me walk you through what probe deployment would actually look like if it were occurring. First, there would be a separation event. Atlas, which current observations treat as a single object, would split into multiple components. One component continues on the primary comet trajectory. Other components diverge, following slightly different paths. Initially, these components would remain close together, appearing as a single elongated smudge to telescopes. But over days and weeks, the separation would become apparent. Observers would detect multiple distinct nuclei instead of one. Spectroscopic analysis might show different composition signatures if the separated objects have different surface properties. And trajectory calculations for each component would reveal they're heading toward different destinations, perhaps one toward Venus, one continuing on the original path, others potentially directed toward Mars or Jupiter. Has this been observed? No. Current observations treat Atlas as a single coherent object. There have been no reports of fragmentation, no detection of multiple nuclei, no trajectory divergence. Does that mean probe deployment hasn't occurred? Not necessarily. It depends on timing and scale. If separation happened recently, the components might still be too close together to resolve as distinct objects. If the separated probes are small meters across rather than kilometers, they might be too faint to detect against the brightness of the main nucleus and coma. Observational limitations matter. Just because we haven't seen something doesn't mean it isn't there. It might mean our instruments aren't sensitive enough or weren't pointed at the right place at the right time. But this is where I have to plant a flag for intellectual honesty. The burden of proof lies with the claim, not the null hypothesis. If someone claims Atlas has deployed probes, they need to provide evidence, detecting multiple objects, measuring divergent trajectories, capturing spectroscopic signatures that differ from expected cometary composition. Absent that evidence, the default assumption is that Atlas is what it appears to be, a comet. An unusual comet with a statistically improbable trajectory, yes, but a comet nonetheless. Speculation is valuable for generating hypotheses, but hypotheses need testing, and until observations confirm probe deployment, it remains in the category of physically possible but unproven. Now let me take this one step further into even more speculative territory, and I want you to understand I'm doing this to map the boundaries of possibility, not to assert belief. If probes were deployed toward Venus, what would their purpose be? 3 possibilities exist within the framework of scientific plausibility. 1. Sample return. A probe could collect atmospheric samples from Venus's upper atmosphere or surface material if it lands, then return that material to Atlas or a rendezvous point for later retrieval. This is technologically challenging but not impossible. We've done sample return missions to asteroids and comets. Scaling it to Venus from an interstellar origin point raises energy requirements, but the low delta velocity windows make it more feasible than it would be from most trajectories. 2. Observational platform. A probe could position itself in Venus orbit or on a flyby trajectory that provides close-range observations of the planet's atmosphere, surface, and magnetic environment. Data collected could be transmitted back to Atlas, to Earth, or stored for later retrieval. Again, technologically complex but within known physics. 3. Biological delivery. This returns to the directed panspermia hypothesis. If an advanced civilization wanted to seed planets with life or biological precursors, delivering payloads to multiple planets within a single system maximizes success probability. Venus's surface is inhospitable, but its upper atmosphere has been identified by some astrobiologists as potentially habitable. A probe carrying extremophile microorganisms or complex organic molecules could, in theory, deliver them to that atmospheric layer. Would this constitute life as we know it? Would it even be detectable? These questions move beyond physics into biology and philosophy. I'm presenting these scenarios not because I believe they're happening, but because they're the logical extensions of the Atlas as artificial probe hypothesis. If you're going to seriously consider that hypothesis, you have to consider what such a probe's mission would be. And these three options, sample return, observation, and biological delivery, represent the scientifically plausible purposes. They don't require faster-than-light travel, exotic physics, or violation of thermodynamics. They just require technology somewhat beyond what humanity currently possesses, and the will to undertake multi-million-year interstellar missions. But now let me bring us back to solid ground. All of this speculation rests on an unproven premise, that Atlas is artificial, and the evidence for that premise is circumstantial at best. Unusual trajectory pattern? Yes. Low delta velocity windows? Yes. Statistical improbability? Yes. But none of these individually or collectively prove artificial origin. They prove unusualness. And the universe is vast enough that unusual things happen naturally with some regularity. So where does that leave us on November 3? It leaves us with an observational opportunity. If probe deployment is occurring, the Venus encounter period is a likely window for it. The geometric conditions are favourable. The energy costs are minimised. If we're going to detect evidence of artificial behaviour, now would be the time. But if we observe nothing unusual, if Atlas passes Venus with trajectory changes that perfectly match gravitational models, that doesn't definitively rule out artificial origin. It just means that if Atlas is artificial, it's not revealing that nature through behaviours we can currently detect. This is the uncomfortable space where science operates when dealing with unprecedented observations. We can't prove a negative. We can't prove Atlas isn't artificial any more than we can prove it is. We can only accumulate evidence that weighs more heavily toward one interpretation or another, and November 3rd adds one data point to that accumulation. Not the final answer. Just another measurement in an ongoing investigation that will continue through the December Earth approach and the March 2026 Jupiter encounter. Each observation refines our understanding, narrows the range of possibilities, and moves us incrementally toward conclusions we can defend with confidence. Let me tell you exactly where we are in time. As I'm writing this section on October 31, 2025, we're approximately 72 hours from 3I Atlas's closest approach to Venus. 61 hours from a moment that's been calculated, predicted, and anticipated since the moment this interstellar object's trajectory was confirmed. And in those 61 hours, everything we've discussed is trajectory mathematics, the delta velocity physics, the gravitational interaction scenarios, the speculative possibilities, all of it transitions from theoretical to observational, from what could happen to what did happen. And that transition is why I needed to make this video now, before the encounter, before the noise of competing interpretations and preliminary reports makes clear thinking difficult. So here's what's going to happen over the next 72 hours, and here's what you should be watching for. First, understand the timeline. November 3rd, 2025 at 11:47 a.m. Universal Time is the moment of closest approach, 0.65 AU from Venus. Convert that to your local time zone. If you're in Eastern Standard Time, that's 6:47 a.m. Pacific Time, 3:47 a.m. Pakistan Standard Time, 4:47 p.m. Mark it on your calendar, not because you'll see anything visible from Earth's surface you won't, but because it anchors the sequence of observations that follow. Ground-based telescopes that have been tracking Atlas will continue observations through the encounter period. Those observations won't be broadcast live like a rocket launch, but data will be collected continuously. And within hours to days, that data will start appearing in online databases, amateur astronomy forums, and eventually official announcements. Here's specifically what to watch for in the observational data. Brightness changes. If Atlas's brightness increases significantly during or immediately after the Venus encounter, that indicates increased outgassing activity. The mechanism could be solar heating, stress from gravitational tides, or in the most speculative scenario, artificial activity. Brightness is measured in astronomical magnitude, and typical comets can vary by several tenths of a magnitude as they pass through perihelion. If Atlas shows a brightness spike larger than expected, That's anomalous and requires explanation. Conversely, if brightness decreases or remains stable when models predict an increase, that's also anomalous. Either deviation from prediction tells us something about what's actually happening to the comet's nucleus. Velocity measurements. This is perhaps the single most important data point. Astronomers will measure Atlas's position before and after the Venus encounter with extreme precision. From those position measurements, they'll calculate velocity, both speed and direction. Those calculations will be compared against predicted values derived from gravitational models that account for Venus's mass and the geometry of the encounter. If measured velocity matches predicted velocity within error margins, that confirms standard gravitational interaction. If there's a discrepancy faster or slower than predicted, direction changes larger or smaller than calculated, scientists have to explain why. And the explanations will start with the most prosaic possibilities. Atlas's mass was estimated wrong, outgassing was stronger than modelled. Solar radiation pressure had a larger effect than calculated. Only if those conventional explanations fail to account for the discrepancy do we move toward more unusual hypotheses. Spectroscopic data. Spectrographs split light into component wavelengths, creating a spectrum that reveals chemical composition. Different molecules absorb and emit light at characteristic wavelengths, creating a unique fingerprint. By analysing Atlas's spectrum, scientists can identify what gases are present in its coma water vapour, carbon monoxide, carbon dioxide, cyanogen, and various hydrocarbons. If the spectrum changes during the Venus encounter, if new emission lines appear or existing ones strengthen or weaken, that tells us the comet's activity level changed. And again, we look for whether those changes match predictions. Comets approaching perihelion typically show increased water vapour and volatile gas emission. If Atlas's spectrum behaves consistently with that pattern, it's behaving like a normal comet. If not, we ask why not. Fragmentation evidence. Telescopes will be looking for any sign that Atlas has split into multiple pieces. Fragmentation appears as an elongated or multiple peaked brightness distribution rather than a single point source. High-resolution images might resolve distinct nuclei. Astrometric measurements might show position discrepancies indicating material has separated. If fragmentation is detected, the next question is, when did it occur? Before the Venus encounter? During? After? And what caused it? Structural weakness? Tidal stress from Venus's gravity? Outgassing-induced spin-up that exceeded the nucleus's tensile strength? Each possibility has different implications for what Atlas is and how it's behaving. Now let me tell you where to find this information as it becomes available, because you don't have to wait for media coverage or official press releases. You can access the data directly. First source, NASA's Horizon system. This is a web-based interface that provides position, velocity, and orbital element data for solar system objects, including comets and asteroids. In the days following November 3rd, Horizons will be updated with post-encounter trajectory data for Atlas. You can access it at ssd.jpl.nasa.gov/Horizons. The interface isn't particularly user-friendly if you're not familiar with orbital mechanics terminology, but it's the authoritative source for trajectory information. Second source, the Minor Planet Center's database. The MPC collects and publishes astrometric observations from observatories worldwide. When someone measures Atlas's position on November 3rd or 4th, they submit that measurement to the MPC. Those measurements get aggregated and orbital elements get updated. You can follow those updates at minorplanetcenter.net. Again, the data is technical, but it's public and real-time. Third source, amateur astronomy forums. I specifically recommend Cloudy Nights, which has an active comets section, and the MPML, Minor Planet Mailing List, archives. Amateur observers who image Atlas post their results, discuss what they're seeing, and often notice things before official announcements. Twitter hashtags 3iAtlas, Interstellar Comet, and Venus Encounter will also aggregate real-time discussion. Fourth source, arcivd.org's astrophysics section. This is where scientists post preprint papers before peer review. If someone observes something unusual about the Venus encounter, they'll likely write it up and post it to ARXIV within days to weeks. You can set up email alerts for papers containing keywords like 3iAtlas or Interstellar Comet. Fifth source, ESA and NASA official communications. ESA operates several social media accounts for its missions and science programs. NASA's Asteroid Watch and JPL accounts provide updates on small body observations. These will be more polished and less technical than the raw data sources, but they'll lag behind by days to weeks. Choose based on whether you want immediate technical data or accessible summaries. Now let me manage expectations about what November 3 will and won't tell us. It will provide one data point, one measurement of trajectory, brightness, spectrum, structure. That single measurement is valuable, but it's not definitive for answering the big questions about Atlas's nature. If nothing unusual is observed, that doesn't prove Atlas is purely natural. It just means that whatever makes it unusual isn't manifesting in observable ways during the Venus encounter. If something unusual is observed that doesn't prove artificial origin, it means we need better models to explain natural behavior. The Venus encounter is one chapter in a longer story. December 19th, Earth closest approach at 180 AU is the next chapter. March 2026, Jupiter encounter at 0.36 AU is the chapter after that. Only by observing the entire trajectory, accumulating multiple measurements, comparing predictions against observations across all three planetary encounters, can we start drawing reliable conclusions. But here's why November 3rd specifically matters more than just being another data point. It's the first major planetary encounter after perihelion. Mars was October 3rd, before perihelion. Venus is November 3rd, after perihelion, when the comet has been subjected to maximum solar heating and is still in a highly active state. If outgassing or other dynamic processes are going to produce observable effects, this is the time. Additionally, Venus's gravitational influence is stronger than Mars's but weaker than Jupiter's. It's a Goldilocks encounter significant enough to matter, but not so overwhelming that it masks subtle effects, and the observational geometry is favourable. Multiple spacecraft have line of sight. Ground-based telescopes can track Atlas through the encounter period without solar interference. We have the capability to collect high-quality data. Whether that data reveals anything unusual is the question we're about to answer. Let me talk about what happens after November the 3rd, because the story continues. Between November 3 and December 19th, a span of 46 days, scientists will be analysing Venus encounter data, refining trajectory models, and preparing for the Earth approach. And here's what makes December 19th interesting. It's not a close approach by Venus standards. At 180 AU, approximately 270 million kilometres Atlas will be far from Earth. But it's the closest the comet comes to our planet, and that proximity enables observations that aren't possible at greater distances. Ground-based telescopes will have their best views. Radar systems might be able to bounce signals off the nucleus and get direct measurements of size, shape, and rotation rate. Spectroscopic observations will be more detailed because the geometry improves signal-to-noise ratios. And then March 2026, Jupiter. The final planetary encounter before Atlas exits the inner solar system and returns to interstellar space. At 0.36 AU, from Jupiter approximately 54 million kilometres, this is closer than the Venus encounter. Jupiter's gravitational influence will be substantial. If there's going to be a major trajectory alteration, if Atlas is going to reveal unusual behaviour, the Jupiter encounter is the most likely time, and we'll have multiple spacecraft observing not just JUICE, which will be closer to Jupiter by then, but potentially Juno, NASA's Jupiter orbiter, and ground-based instruments. The data from that encounter will be the most comprehensive of all three planetary approaches. So November 3 isn't the climax, it's the beginning of Act 3. Act 1 was discovery and initial characterization. Act 2 was the approach to perihelion and the Mars encounter. Act 3 is Venus, Earth, Jupiter, and eventually the exit from the solar system. And we're fortunate enough to be living through Act 3 in real time, with the capability to observe and analyse as events unfold. This is genuinely historic. Interstellar objects are rare. We've confirmed only 3 in human history: Oumuamua in 2017, 2I Borisov in 2019, and now 3I Atlas in 2025. Each one teaches us something about the population of objects drifting through interstellar space, their compositions, their trajectories, and if we're willing to seriously consider the possibility whether any of them might be artificial. Here's what I need from you over the next few days. Watch November 3, not passively but actively. Check the data sources I've mentioned, look for updates, read what amateur observers are reporting, compare preliminary findings with pre-encounter predictions, and think critically about what you're seeing. Don't immediately jump to aliens if something unusual appears. but also don't reflexively dismiss anomalies as instrument error or bad data. Examine the evidence, weigh the competing explanations, update your beliefs based on what observations actually show, not what you want them to show or what feels comfortable believing, and then join the discussion. Post comments with your observations. Tag this video if you find interesting data. Contribute to the collective understanding of what happened. Because science isn't just something that happens in laboratories and universities, it's something we all participate in when we observe the universe carefully, think rigorously about what we observe, and share our findings with others. November 3rd, 2025 is your invitation to participate. Don't miss it.